So this section is about continuity definition. I kind of touched on it when I talked about the types of discontinuities, but I really want to emphasize the way you prove a discontinuity or the way you prove continuity. So the continuity test is the definition of continuity. Your function is continuous if and only if, first of all, your function has to exist at the point. Secondly, your limit has to exist, which again means that your limits as x approaches c from the positive direction has to equal your limit as x approaches c from the negative direction. And the limit and the value of the function have to be the same thing. So all three of those things have to be true in order for the continuity, a function to be continuous. They're written this way because they're kind of in order of how easy it is to find these things. So f of c is probably the easiest thing to find. The limit is the next easiest, and then checking to see if they're equal is the last step. So here's an example. I want you to think to yourself, where is this function discontinuous? And which part of the continuity test fails? And then we'll talk through it. So go ahead and attempt it on your own, and then we'll talk about it. Okay. So I see three places where we have a failure to be continuous. So we have x equals -1. We have x equals 0, and x equals 1. Those are places where if I graph this function, I have to pick up my pencil. So those are places where you have a discontinuity. So if I look at x equals -1, part 1 of the test says f of 1 exists. Yes, f of -1 exists. Yes, f of -1 exists. It's right there. It's at 0. So yep, that's true. The second part of the test is the limit as x approaches -1 of f of x exists. And that's where we fail on this one, because the limit as x approaches -1 from the positive direction is 0, and the limit as x approaches -1 from the negative direction is 3. So this is where we fail. The limit does not exist because the limit as x approaches -1 from the negative direction is not equal to the limit as x approaches -1 from the positive direction. Sorry, my pen is acting weird. Okay. Now, if I look at x equals 0, I could say, well, f of 0 does not exist. So at the very first step, this one fails to be continuous, and that's the justification for it. So that's where we've got, no, it's not continuous because f of 0 certainly doesn't exist. Okay, x equals 1. If I look at f of 1, that does not exist. So we're done with that. But I want to point out that for this particular one, the limit does exist. So the limit as x goes to 1 of f of x exists. And it is like 2. So it exists and it's a number. That's the sign of a removable discontinuity. If your limit exists, but your function, it doesn't match it, that's a removable discontinuity. All right, so we're going to do this example. This is asking, is our function continuous at x equals 0? And is it continuous at x equals 3? Okay, so at x equals 0, I'm going to start there. F of 0, well, if I'm actually at 0, I would use sine of 0 as my evaluating that function. So f of 0 is 0. If I want to know the limit as x approaches 0, I need to check, because this is a piecewise function, I need to check from both directions. So from the negative direction, the limit as x approaches 0 from the negative direction, that would be the sine of x part of the definition. And so sine of 0 would be 0. And then I'm going to check the limit as x approaches 0 from the positive direction. Well, that would be 2x part of the function, but that would also be 0. So these two limits match. Oops, I drew a sad face, but I was really happy. And they're equal to the value of the function. So x equals 0 is a point of continuity. Yes, it's continuous at x equals 0. It passes all three parts of the continuity test. Now I'm going to do x equals 3. So f of 3 would be 3 squared minus 4, which would be 5. So that's a good start. And then I need to check the limit as x approaches 3 from both directions. Well, if I'm a little bit smaller than 3, I would use 2x. So I would get 6. And if I'm a little bit bigger than 3, I would use x squared minus 4. And so I would get 5. These two do not match. So this is not continuous at x equals 3 because the limit fails to exist. So the answer for this part is no.